Okay, so hello everyone. So we are going to solve today another problem, which is an algebraic equation, which is slightly perturbed by a small number. As usual, we note this one epsilon, which is much smaller than 1, assumed to be positive here. And in this question, which was asked in a test in March 2019, it is asked to find a two-term expansion for all three roots of that equation when first alpha is equal to 1, second, alpha is a small number of order epsilon, and third, alpha is an even smaller number of order epsilon to the power p, with p larger than 1. So you can just figure out the last option as alpha being, for instance, of order epsilon square. All right, so let's start with the first problem. Alpha is equal to 1. Alpha is equal to 1 means that the governing equation becomes something like this. We can just simplify out. This is equal to 0. And we need to find then two-term expansions for the three roots of that equation. So we can first think it should have become now a natural reaction to start with the unperturbed problem. And the unperturbed problem is what you get when you replace epsilon by 0. This is x squared plus 2x plus 1, meaning that x is equal to minus 1 is in fact a root with a multiplicity 2. Okay, so we need to be careful when we see a root with a multiplicity equal to 2, because it means root splitting as soon as we consider the perturbed problem. So it means that the right sequence might not necessarily be a sequence in epsilon. All right, however, it's maybe just very quick to check whether that sequence is fine or not. So I'm going to seek the first two roots, which correspond to the regular roots. Of course, why do we have two regular roots? We should probably then classify the problem as regular or singular. Just take a minute to think about it. But because the equation we want to solve is such that the highest derivative here is multiplied by 3, it means that the unperturbed problem has only two roots, or one with multiplicity 2. So it means that we have lost one root somewhere. Okay, so this means that the problem is singular. We should expect two roots near minus 1 and one root near plus or minus infinity. Okay, let me allow to write this. Strictly speaking, this is a little bit difficult to say that a root is near infinity. I just want to mean that as epsilon goes to 0, this root is going to plus or minus infinity. All right, so we can first focus on the first two roots, which could be captured with a regular ansatz. And the other one will require a rescaling. All right, but we'll take care of the second one a little bit later. That's for the program. So let's start with the two roots near minus 1. And as I was explaining before, it doesn't hurt probably too much to start with a regular sequence. Try an ansatz with sequence in the basis like epsilon, epsilon squared, epsilon to the third, and so on. Which means that we are seeking a solution in the form x is equal to minus 1. So we do expect, of course, that x0 is equal to minus 1, but to remain general, we can keep x0 here. Then the next term would be epsilon x1, then we have epsilon squared x2, and so on and so on. We are requested to keep two terms, so actually x1 will be enough. Okay, because I think this was a question that was asked during a test. They don't want to make it too long for you. And this is why I just required for you to keep only the first two terms. So what we do next is we substitute this and that in the governing equation. So we have epsilon x to the third will provide epsilon x0 plus to the third 3 times x0 square x1 epsilon plus something of order epsilon, which I don't, epsilon square, which I don't want to make explicit here, because this epsilon square and this epsilon here will give me something of order epsilon to the third, and definitely I don't want to keep that. Even this one probably and certainly will drop, because we are just interested in leading order plus order in epsilon. So it means, you see, we could already have skipped this second term. Let me just underline it like this to indicate that in principle this one should drop. Then second term is x squared, so it's gonna give x0 square plus twice double product, okay, plus something of order epsilon square, which I don't write here, plus 2 minus epsilon multiplied by x, x0 plus epsilon x1 plus 1, and this is equal to something of order epsilon square as I dropped it. All right, so we can collect now the terms having similar powers. At leading order, which is order 1, we have x squared, we have 2x0, and we have 1. All right, so let's just write this clearly here. Plus 2x0 plus 1 is equal to 0. And the solution, of course, of this is x0 is equal to minus 1. All right, nothing amazing, of course, because this is the same solution as the unperturbed. We should be familiar with that now. Let's see, it might be a little bit more tricky at the following order, because we could expect something like 0 is equal to 1, like what we have seen in a previous video when there was a root splitting. All right, so let's be careful here. What do we have? We have one term coming from here. Then there will be another one coming from here. There will be two mixed products here, and that's pretty it. So if we make it now clear, x0 to the third plus twice x0 x1 plus twice x1 minus x0, and this is equal to 0. Okay, what can we say out of that? X0 to the third, this is minus 1, because x0 is equal to minus 1, minus the last term, x0, this is plus 1. All right, so these two, they cancel out. And what we have in the next equation is just something like let me keep going. Twice x0 plus 1 multiplied by x1 is equal to 0. And this, in fact, okay, this is what I was getting. This is equal to 0, which means that this equation is just trivially satisfied. And we should be, of course, happy about it, because it means that when we have root splitting, you remember when we get the right sequence, there was an intermediate order at which the equation is trivially satisfied. And unfortunately, in order to determine x1, the only chance is to go to the next order. All right, so we should have done a job a little bit more accurate earlier, because I need now to keep terms of order epsilon square. All right, so we need to review what we did before. The term here that is underlined here is already epsilon square, so it's good that we kept this one. I'm going now to add terms that I missed before, and So in here, what we missed is something coming from x squared, and x squared will provide epsilon square x1 square plus twice x0 x2 epsilon square. Okay, that's a little bit more complicated, and here we have plus epsilon square and x2. All right, so if we reconsider now the different terms at order epsilon square, what we have 3x0 square x1 coming from the first term. Then we have these two terms coming here from the x square. So plus x1 square plus 2x0 x2 times epsilon square. And then what do we have from the last term? We are looking for terms in epsilon square. So we have 1 here multiplied by this, and we have 2 multiplied by that. So we have 2 extra terms over there. So plus 2x2 epsilon square and minus x1. And this should be equal to 0. All right. Let's first have a look at the terms related to x2, and we recognize exactly the same pattern as what we had before, meaning that because x0 is equal to 1, these two terms, actually, they will vanish. And what we are left with is 3x0 square. This is equal to 3 times x1 minus 1, so we have 2x1 plus x1 square is equal to 0, which means x1 multiplied by 2 plus x1 is equal to 0. So it means that we have x1 is equal to 0 or x1 is equal to minus 2. Okay, we were asked to get a two-term expansion. So we got at least one, because it means that if we use this, it means that at least we have one root, and the root is x is equal to minus 1 plus epsilon times x1. So that means minus twice epsilon plus something of order epsilon square. The other one actually doesn't provide a second term, because what we get here is x, let me just call them xa for the first root, xb for the second root, is equal to minus 1. And what we can just say here is that we have something plus order epsilon square. And so we do not really answer the question here, because this is only a one-term approximation. All right, but you might already have observed probably that in fact we could go with a higher expansion in order to determine x2 and then x3 and then x4 and so on. But we would realize that the values that we compute for x2, x3, x4, all of them are equal to 0. And in fact, you probably observed that if you return to the original equation, which is the equation shown here at the top, if you replace x by minus 1, what you end up with is minus epsilon here, plus 1, twice minus epsilon multiplied by minus 1, plus 1 equals 0. And this is trivially satisfied, meaning that in fact, x is equal to minus 1 is also a root of the perturbed problem. So it means this is a root of the unperturbed problem, but this is also a root of the original equation. Okay, so there's no way to provide a second term, and the way to write this is just to drop to indicate that we have an exact root to the problem. Okay, second, we can focus now on the large roots. So we do expect a root that is large. Let me just copy this again so that we can keep it with us. Okay, what we are interested in now is to find the large root of that problem. And to do this, we should introduce a rescaled version and say, okay, x is equal to, because we have a large root, something of order 1 divided by epsilon to a certain power. Let me just write epsilon to the power q, and q should be a positive number. So for instance, can be 1 over epsilon square, which would all of them provide large values. Okay, and the first task is to determine q, so the order of magnitude of that root. And to do so, maybe we can practice here the method called pairwise comparison, which says that we need to compare 2 by 2 the different terms of the equation. And so here in this case, we can identify 4 terms, and the job is maybe not too tough, because what we need to do is just to find one balance. So if we are quite lucky, maybe if we do the right tests, or if we find the right combination at the first trial, then we get the right order of magnitude. And so let's try, for instance, by comparing the first 2 terms. Okay, this is something that usually works quite well. Or the last 2 terms is also something that works quite well. And if we say, for instance, let's assume that epsilon x to the third has the same order of magnitude as x squared, and both of them lead, meaning that they are at least 1 order of magnitude larger than the other remaining terms, or I should say rather that no other remaining term is larger than these guys. So what do we have? We have, it means that epsilon x is of order 1, meaning that x is of order 1 over epsilon. Okay, we need to check now that this is fine. The first term, which is epsilon x to the third, will be of order 1 over epsilon squared. The second term, which is x squared, will be of order 1 over epsilon squared. Okay, of course, they both match. And this is exactly actually what we started to write. Then the next term, T3, is 2 minus epsilon multiplied by x. So because epsilon here with the 2, epsilon here is much smaller than 2, the leading solution is 2. And so we have 2 over epsilon, which is indeed T3 is indeed smaller than T2 and T1. All right, so we are fine with that. And T4 is equal to 1, which is also, of course, much smaller than T1 and T2, which are huge numbers, because T1 and T2, their order of magnitude is 1 over epsilon squared. Okay, so something very large. So in fact, we got it. So we got the right scaling. So the right scaling is x is x tilde over epsilon. So we need to substitute this in the governing equation. We should expect to multiply the governing equation by epsilon squared in order to get something of order 1 in the governing equation, all right? Because that's the order of magnitude of the leading terms. All right, but we can do it in full detail so we understand exactly what's going on. So epsilon multiplied by x tilde to the third over epsilon to the third. So you see, this is of order 1 over epsilon squared. So we will have to multiply by epsilon squared afterwards, plus x tilde over epsilon squared. Same story for this guy. 2 minus epsilon multiplied by x tilde over epsilon plus 1 is equal to 0. All right, so let's just multiply now by epsilon squared in order to rewrite the problem in such a way that each term in the equation has order 1. Okay, this is typically what we should do in order to make sure we keep control of the different orders of magnitude of the different terms in the problem. So we end up with x tilde to the third plus, I might have forgotten a square over here. Yep, x tilde square 2 minus epsilon x tilde plus epsilon square, and this is equal to 0. Now we have done our rescaling properly. We can substitute or use a regular ansatz, to get or to determine x tilde. So we can say x tilde is equal to x0 plus epsilon x1 and so on, hoping that just these two terms will be enough to do the job. All right, so if we substitute the ansatz in the governing equation, what we have is x0 to the third, 3x0 squared x1, plus terms of order epsilon squared that I'm just dropping now, x0 squared twice x0 x1 times epsilon plus 2 minus epsilon x0 plus nothing is equal order epsilon squared. Now we can collect the different terms with respect to their order of magnitude. And so at leading order, we have this is equal to 0. So meaning that we have two options, either x0 is equal to 0 or x0 tilde is equal to -1. Okay, this one, the first one, needs to be rejected. Why? Because x0 tilde needs to be different from 0. Because if it was equal to 0, it means that the sequence we have chosen would be chosen here, starting with the first term being of order epsilon. And if the first term is of order epsilon, in x tilde, you see that we are seeking solutions for x that are of order 1. So they are not large roots, and it does not correspond to what we want to do, all right? So typically if you use a rescaling, the first term in the regular ansatz should not be equal to 0, otherwise you completely spoil the rescaling that you did. All right, so and in fact, we are very happy with just one root over here because we are just missing one root of the original problem. All right, so everything is fine, and this is exactly what we should expect. The next contribution will be 3 x0 square x1 tilde plus twice x0 x1 and then plus 2 x0, and this is equal to 0. So we have here 3 minus 2, 3 minus 2, so that's 1. Is equal to minus 2x0, meaning that x1 is equal to 2. And we are happy, the problem is closed. We have found the second root, which is -1 over epsilon plus 2 plus additional terms that are of order epsilon. All right. Good. So I hope this was clear. The logic is quite straightforward, but you need, of course, to practice a little bit to make sure you can do this by yourself easily. We can tackle now the second question. The second question is do the same, but assume that alpha is a small number. I'll just copy the question here, paste it. All right, and so we have second question, same, but alpha is something that is of order epsilon. Why is it important to be able to solve these problems? Because, for instance, this governing equation you have here is an algebraic equation, could be, for instance, the characteristic polynomial of a linear differential equation. And you know that the roots of a characteristic polynomial will just provide the time scales and the length scales in a problem. And so if you want to understand in a certain problem the different length scales, the time scales, depending on the values of the parameters, then it's important to be able to solve these type of equations. All right, so everything we do here is keeping in mind that we have to solve such problems, and it's important sometimes to be able to solve perturbed algebraic equations. All right, so if alpha is something that is of order epsilon, let me just rewrite alpha is equal to another symbol. Let's probably use alpha tilde, or let's use alpha bar times epsilon, and say alpha bar is equal to, is of order 1. Then if we substitute this in the governing equation, what we have is something like this. Great, and we need to solve that equation. All right, so what changes? Well, let's start again from scratch, I would say, and let's first have a look at the unperturbed problem. And it is important to say in this case, or at least to observe in this case, that the unperturbed problem is something different. Is something different because it's only first degree. So we should expect in this case one root which is of order 1 in the neighborhood of -1/2 plus 2 large roots. All right, so we can start with a root which is root near x is equal to -1/2. And let's try with a regular ansatz. Okay, again, it doesn't hurt too much to try this. And if it doesn't work, we'll try to see if something else can save us. So if we push this into the governing equation, we have epsilon times x0 to the third plus something of order epsilon squared that I'm going to momentarily drop because I want to focus only on the first two terms, plus epsilon alpha bar x0 square plus 2, I can split right on, to epsilon x1 minus epsilon x0 plus 1 is equal to 0. And so at leading order, we have the same as the unperturbed. All right, so twice x0 plus 1 is equal to 0, meaning that x0 is -1/2. Okay, nothing that should be unexpected here. And then at the next order, we'll have minus epsilon over 8. I will replace right away, plus alpha bar over 4. Sorry, I will just remove epsilon here. This is 1, okay, because we're talking about the coefficients of epsilon, plus alpha bar over 4. Then the next term will be plus twice x1, and then plus 1/2. And this is equal to 0. All right. The solution to that equation is, okay, probably we should put everything on the same denominator. And if we put everything on the same denominator, which would be 8 to x1 plus 4 minus 1, that's 3, plus 2 alpha. And this is equal to 0. So it means that x1 is equal to -3 plus 2 alpha bar over 16. And we got the root. Okay, so the root is x Let me just again use ABC to indicate we have 3 roots. Okay, battery is running low. Minus 1/2 minus 3 plus 2 alpha bar over 16 times epsilon plus terms of order epsilon square. Okay, now it is important here to notice that you have chosen to, or we have chosen to use an intermediate parameter, which is alpha bar, okay, which was not in the original problem. So it's important to replace it by its original value. And so we have minus alpha bar was defined as alpha over epsilon. All right, so we have alpha here over 8 and minus 3 epsilon over 16 plus terms of order epsilon square. All right, and that's pretty it. This is the expression of the first root. Okay, second root, we need to find the order of magnitude of the large root. So find large roots. All right, so first is to get the right scaling. Okay, find the right scaling or rescaling, because we want to say that x is equal to x tilde over epsilon to a certain power. Maybe we can use again pairwise comparison. Pairwise comparison. And see if we can get something out of that. All right, so in the equation, the governing equation here, I need to compare the different terms 2 by 2. Let's try again with the first 2 terms. Why not? It would say something like epsilon x to the third plus epsilon alpha tilde, alpha bar x square. Oh, sorry, they have the same order of magnitude. We simplify out by epsilon. We can simplify out by x. And we find that x has order of magnitude alpha tilde, which itself is 1. And it means that the roots that we get in this case are roots which are of order 1. And this is not interesting because that's just the root we got before. Probably could be the root that we get before, provided these 2 terms are leading. Okay, so this is not the right balance. We're looking for large roots. Okay, let's try first and third. Epsilon x to the third has same order of magnitude as 2 minus epsilon times x. In fact, this one can just drop, okay, because it's small compared to 2, and we are just comparing orders of magnitudes, which would mean epsilon x square is of order 1, or x is of order 1 over square root epsilon. Okay, not too bad. Let's try to see now. We need to check whether we were right or not. The first term is epsilon x to the third will be order epsilon times, x to the third. So we have in the denominator epsilon square root epsilon, which is 1 over square root epsilon. That's indeed something large. Okay, fine with it. The second term will be epsilon multiplied by alpha bar multiplied by x squared, which is epsilon. Oops, sorry. Which is epsilon. It means something of order 1, which is indeed much smaller than 1 over square root epsilon. Okay, so fine. At this point, we were right to assume that the first and the third term, they could balance each other. The third term, if everything is right, should be of order 1 over square root epsilon, because we stated that T1 and T3 have the same order of magnitude. Will be 2 over square root of epsilon, which means 1 over square root epsilon. And this is fine. Okay, we are happy with it. And the last term, T1, is 1, which is much smaller than 1 over square root epsilon. So it means that we have at least found one order of magnitude. Okay, so it means that at least there will be one root. We're still missing two roots, right? But at least there will be one having that order of magnitude. Okay, so let's see if we have 1 or 2 by starting rewriting the problem with that scale, and see if we have 2 roots, then the problem is solved. So the right scaling is x tilde over square root epsilon, or now we can use this to substitute in the original equation, which I'm going to copy here to get it a little bit closer. So what we have is epsilon multiplied by x tilde to the third, epsilon square root epsilon, plus epsilon alpha tilde, x tilde square over epsilon, plus 2 minus epsilon, x tilde over square root epsilon, plus 1 is equal to 0. The simplify here, we see that we have two leading terms. They have order of magnitude 1 over square root epsilon. So we multiply out everything by that quantity in order to obtain an equation with leading order terms of order 1. And what we have here is this, plus square root epsilon is equal to 0. All right. This is probably slightly different from what we have ever encountered, in the sense that you see that we have square root epsilon coming here. And if you want, this is a problem that we could rewrite in this way. Let me just call square root epsilon, let me just call it this epsilon, okay? This is a new symbol. Square root var epsilon, like this. X tilde square plus 2 minus this new epsilon squared plus this new epsilon is equal to 0. We are maybe much more usual to use that form of equation, which can be solved with a sequence starting with a regular ansatz and a sequence that is like this, right? Okay, that's if you don't feel too much familiar with what I'm going to do, that's something you can, of course, proceed with. So, of course, you're allowed to redefine the small number epsilon and end up with something that looks like that. Okay, but this is not what I'm going to do. I'm going to right away. So observe that the sequence could be 1 square root of epsilon, epsilon itself, and so on and so on. Okay, so we are going to seek a solution that is x0 plus square root epsilon times x1 plus higher order terms. And of course, because we did a rescaling, again, we must assume that x0 tilde is different from 0. Okay, let's just have a look. We can have a look at the unperturbed problem first, or we can go right on with the substitution. Of course, we do expect that at leading we'll recover the same as the unperturbed. So if you're really curious and if you're impatient to see exactly what it's going to do, what it's going to provide, you can have a look at the unperturbed. Okay, it's never bad to do it. It is, at least it's going to tell us whether we'll have 2 more roots or not. X squared, x tilde to the third plus twice x tilde is equal to 0. So we'll have x tilde is equal to 0, which is something we are not interested in, otherwise would not have we would not have a rescaling. And so it means that the unperturbed solution x is plus or minus I times the square root of 2. All right, so complex imaginary numbers. Okay, easy, and we have two roots, so we are happy. It means that this is the only rescaling we have to consider. If you just had obtained here one root, then it means that we have to find another rescaling. So let's keep going. If we now substitute our ansatz into the governing equation, what we have is x0 to the third plus 3 times x0 squared x1 times the square root of epsilon plus alpha bar square root of epsilon x0 tilde square plus 2 x0 tilde. You see that I dropped this epsilon here, which is definitely something of higher order. Twice x0 tilde plus twice square root epsilon x1 tilde plus square root of epsilon is equal to terms of order epsilon that I have not written here. So at leading order, we have x0 to the third, this one, and this one. All right, so same as the unperturbed as expected, of course, plus twice x0 tilde is equal to 0. And so because x0 tilde is different from 0, the two options we have is x0 tilde is equal to plus or minus I square root of 2. Or in other words, the square of x0 is equal to minus 2. Okay, that's what we momentarily had in between. Now we're looking at terms at the following order in square root of epsilon. We have 3 times x0 square means minus 6. All right, the first term here, this is minus 6 x1 tilde plus alpha bar multiplied by x0 squared, so that means minus twice alpha bar, then plus twice x1 plus 1. And this is equal to 0. So it means that 4x1 tilde is 1 minus 2 alpha bar, x1 tilde is equal to 1 minus 2 alpha bar over 4, no matter x0. All right, so we got the other two roots, x, b, and c. They will provide plus or minus I square root of 2 multiplied by 1 over square root epsilon. All right, how do I get up with this? Because this is x0 tilde. All right, and this one enters in the rescaling that we have chosen. All right, it was the leading term in x tilde, and it enters in the rescaling here. All right, so this is why I have 1 over epsilon here. Then the next term will be plus 1 minus twice alpha over 4, and that's it, plus terms of order epsilon here. Again, alpha that we have over there should be replaced by the quantities that had been provided in the statement. So it means minus alpha over 2 epsilon. All right, this is how we decided to redefine alpha. Over there, alpha bar is alpha over epsilon. Okay, so this might be slightly misleading, but keep in mind that alpha over there is a small number. All right, so at the end of the day, this is of order 1. Okay, so all this term is something that is of order 1. Okay, so it shouldn't be a problem. All right, and so we have the other two roots. Good. last part of the problem, what would happen if alpha is even smaller and, for instance, epsilon to another power, to the power p? Well, what would happen if alpha is even smaller? You see we have enough place at the bottom of that page to finalize the problem, the solution of that problem, because if we revisit what we did here, we will just notice that everything we did so far is fine, and it would just repel the order of magnitude for alpha at a higher order, meaning that instead of having here epsilon alpha bar, we would have epsilon to a power that is larger than 1. And if epsilon has a power that is larger than 1, we just saw that alpha is not playing nowhere, is not playing anywhere in the derivation, in the leading order terms, and alpha is just playing in some sort of passive manner. It comes in the equation when we keep going, and so alpha would just disappear from those equations, and what we would obtain is exactly the same, but that term becomes smaller, and it would be just repelled in the following terms. All right, so in the last part of the question, the solution actually is just equal to that. All right, so x, b, c is equal to that. And to be complete, xa, which was computed here before, copy and paste. We need to keep it because we can again remove alpha from that expression, because alpha is something now that is definitely smaller than this epsilon. All right, so I hope it was clear. So you see that with a simple problem at the beginning, and changing the different orders of magnitude of alpha, we can vary the different solutions that we can get. So from large root of order epsilon in the first part, of order 1 over square root epsilon in the second part. All right, so I hope you understood everything, that you enjoyed, and keep going with the following videos. Thank you very much.